We're talking about bitwise operators, which are operators that work directly on bits. You might not use them daily, but they play a big role in graphics, game development, cryptography, and even networking. Those operators are really damn efficient, since by using them you're essentially programming at the lowest level, having full control over your code. Or I guess nearly lowest level. And after all, you're watching a video on C++, so if you're here to optimize your code down to its core bits, or you're just a kid forced by a high school teacher to learn this foreign language, you are in the right place. We'll discuss every relevant bitwise operator and masking, which is their most frequent use case. Now, I suppose you already have some basic knowledge about binary and programming, like converting from decimal to binary numbers, the inverse case, and why this works. So I will start with a quick section that explains how bits are interpreted by computers. You can skip right to the next chapter if you want. At its core, your machine works with voltages, where a voltage can be high or low. It has two values, that's why we call it binary. If we put everything in an electric graph like this, we can set a threshold, where everything that goes below is considered low and everything beyond high. We call the low as 0 and the high as 1. That's how bits come from electricity. Try running int a equals 9. On most compilers, an integer reserves 4 bytes and each byte is 8 bits. For this video we'll stick to 2-byte integers with 16 bits, so we don't fill the screen with a bunch of zeros. You can check this in your IDE's memory storage window by searching for your variable address, in this case %a. You'll see something like 09000000 if you use 4-byte integers. Each pair of digits represents a byte, and each single digit represents 4 bits. The value is shown in hexadecimal, but why? A single hex digit can store 16 values, just like 4 bits can. This makes hexadecimal a compact and efficient way to represent binary data. Most computers are little endian, which means the leftmost byte is the least significant, the rightmost is most significant. A byte is more significant the more influence it has, like if I switch this bit to 1, the representation will be a much greater number. However, by switching this one, it's a smaller difference, so that's why it's weirdly put like this. Take a big endian system for instance, which represents the numbers more logically, I think. Here the most significant byte is this one. The actual order of bits within the byte is always the same. The only thing that changes from computer to computer is the byte order. I wanted to clarify why the order of bits looks like this before continuing. So again, let's reserve space for an integer. First by using int a equals 9, then try using the C++ 14 syntax, int a equals yes. The bitwise operators are just like the regular arithmetic operators, but they work with numbers in binary form, not in decimal form. Let's see how the first two operators work. AND and OR. You know how they function in if statements, right? AND returns true if both conditions are satisfied, while OR does so if at least one is met. The bit operators AND and OR work pretty much the same on bits, that's why they have a similar notation. The AND operator, when applied between two numbers, only selects the bits where both corresponding bits are 1. By selecting I mean setting to 1 in this case. In other words, if you visualize this by columns, you can see how each operation plays out. In this example 1010 and 1100, we first check 1 and 1, we get 1, then we check 1 and 0, we get 0, and so on. If you use the OR operator, you will instead perform an OR operation on every bit. So here is how it plays out. We check 1 and 1, we get 1, we check 1 and 0, we get 1 this time, we check 0 and 1, we get 1, and we check 0 and 0, we get 0. You can try this out on paper or in your mind. Here are a couple exercises. For example, you can pause the video and try solving them and verify your result. But when would you actually use this in day-by-day code? Those operators actually have a couple use cases, but they must be used along with the other operators. We'll get back to those right at the end. The not operator, just like the exclamation mark, it inverts the result. So true becomes false and false becomes true. When using this operator on binary numbers, it inverts every single bit in this manner. The XOR or the exclusive OR works exactly like an OR, but requires only one of the values to be 1. The case where both values are 1 results 0. Again, using bitwise operators, this principle applies to every single pair. It's not really that often used, but hey, now you know how the XOR works at least. But I guarantee you will use the next operators. The shift operators. These ones are probably the most straightforward to use. The left shift operator basically shifts every bit to the left by a given number. Let's visualize it on number 7. Let's shift by 1. Every single bit moves to the left and the last bit becomes 0. The right shift operator works exactly the same but shifts to the right. If we shift the result by 1 back, we get the original number. We can of course shift them by any amount. Note that if you accidentally change the shift bit, the sign bit, the number sign might change. If you analyze the numbers in both binary and decimal form, you might notice that shifting bits to the left will actually double the number. If you shift to the left by 1, it's like multiplying by 2. Also, shifting by 2 multiplies by 4, by 3 multiplies by 8, and so on. I think you see the pattern. We multiply the number by 2 to the power of n, where n is the amount of shifting. The inverse goes for shifting to the right, quite literally. You divide the number by 2 with each shift, and pay attention, we are using integers. The result won't have any remainder, so it's just like using the divide arithmetic operator multiple times. That's the first trick which we're going to discuss now, and it's a pretty useless one, since the compiler already does that for you. When you multiply the number by 2 in C++, the decompose operation in assembly is a bit shift, which means the compiler already optimized it for you. But we've got some pretty useful use cases when using shift operators. I will cover probably the most useful one. Masking. Masking is used quite often when manipulating bits. If you're not familiar with the masking concept, you can view it in 2D. This is our source image. By applying a mask, we are essentially seeing it through a shape. Mask can also be applied not only with shapes, but we're sticking to the basic idea here. We are only seeing a portion of the image. That portion itself is a mask. The same goes for masking binary numbers. If our source image is a number itself, the portion might look like this, where we will see the image through the ones of the mask. Take a look at a couple masks. By masking a binary number, we can select a certain amount of bits. So here is how you get the first 4 bits of a 2-byte integers. To create a bit mask in C++, we start with a number where all the bits are set to 1, which is just tilde 0. Of course, 0 in binary is represented as zeros all the way. Then we shift it left by however many bits we want. Let's say 4. This pushes the ones to the left and leaves the zeros in the lower bits. Next we invert the result. Now we have a mask where only the lowest 4 bits are set to 1 and everything else is 0. Let's write this in a shorter form. Now the important part, applying the mask. Let's create a number to extract the first 4 bits from. Then we do this using the AND operator. Why? Because wherever a mask has a 0, it wipes the corresponding bit in the original number. By wipes, I mean sets it to 0. But where the mask has a 1, the original bit stays the same. That's how AND works. Any bit AND 1 is itself. It's crucial to understand those steps and how we're playing with bits, since this is the fundament of bit manipulation. Masks are probably the most important concept since they allow you to get whatever section of bits you want. For example, if you want to obtain those 4 bits, you shift the number so the bits become the first 4. Then you apply the mask. Hey handsome, I'm Andrei from the future, and I'm here to announce that this video is finally done. The video you just saw took me a lot of time to make, a lot of time to animate, sound design, and I'm excited to see how it goes out. But I guess, yeah, no one really cares about this. But everyone cares about the fact that this entire source code is available on GitHub. And you can find it in the video description, if I don't forget to put it, of course. And I don't know, load it in your computer and start learning from those animations. Maybe you can steal some of them. And if you think that's clever, it is not, because I already stole all of the code before you. So yeah, I'm 2 steps ahead. And that's it. If you have any questions or suggestions, ideas about future videos, I would really appreciate them, because I have no idea what I'm going to post next. And thank you very much for watching. See you next time.